Suppose you have an RGB image. An RGB image would consist of three frames: red, green, and blue. What we're seeing here is an RGB image of size 32 by 32, and the three frames that you see each correspond to red, green, and blue, respectively. We are interested in counting the number of pixels that an RGB image of size 32 by 32 would have. Remember, the 2D image that we see has contributions from red, green, and blue all together to give us a colored image. So when we are interested in calculating the number of pixels, we need to count the pixels in individual channels: the red channel, the green channel, and the blue channel. So we know there are three channels that exist. Each is 32 by 32 in size. So we could calculate the number of pixels in one channel. That turns out to be 1024. The same number of pixels would be present in the next channel and then in the third channel as well. So for a 32 by 32 sized colored image, we would have 3072 number of pixels. Now we'll move to another example here, and then we'll see, and then we'll come back to it. So what we see is a 4x4 image frame, and typically what we want to do in neural network applications when it comes to processing images, we want to vectorize our data, our images. To vectorize the data is simply stacking horizontally or vertically our images. So the first 4 pixels here are put up in an array just like that. The next 4 pixels in pink are then set up in another array in front of that. Similarly, the next 4 pixels are then in blue, are stacked next to it, and then the final 4 pixels as well. So we end up converting our 2D image into a vector. So what we originally had was a 4x4 image. It became a 1x16, 1x16 vector. Keeping track of these vectors is computationally simple, and it's easier to process these vectors instead of having two-dimensional operations. So here is a simple data set of 3 images stacked on top of each other. Each of them is vectorized, and each of them is 1x16. So we could say these are basically 3 images of size 4x4. Now, while we saw some horizontal stacking, it is possible that images could be stacked vertically as well. A simple matrix transpose could make the conversion from horizontal to vertical stacking. But in case these are vertically stacked, remember, you would have 16 rows and 3 columns. The columns are now representing the number of images, and the rows contain the pixel values. The dataset that we are going to look into today is going to have 50 images. So essentially we will be looking at 50 columns, and each column would have 3072 rows. So that means our dataset has 50 32 by 32 colored images. Alright, and we could always have these images stacked vertically, or we could take a transpose and have them stacked horizontally. Right, so we could manipulate our dataset to our liking and to our application. The problem at hand is that we want to have a test image. We want to have any image. We could download an image from the internet, but whatever image that is, we are going to refer to it as a test image. We want to find the closest match of the test image in our dataset. So what image in our dataset is the closest, is the most similar to the test image? Now there are multiple ways we can define similarity, but one way to define similarity is on the basis of Euclidean distance. So Euclidean distance is one feature through which we could figure out how similar two images are. On my left hand side we see our test image. On the right hand side we have our data set containing 50 images. What we want to do is we want to find the Euclidean distance of our test image with an image from the dataset, and we want to arrive at an answer for Euclidean distance. So we want to find the Euclidean distance of our test image to the first image of the dataset, then Euclidean distance of our test image to the second image, Euclidean distance of our test image to the third image, and so on. So we want to find Euclidean distances of our test image with all of the images in the dataset, and the one that gives us the smallest Euclidean distance would in fact be the most similar to our test image. Why would that be the case? Precisely because in Euclidean distances we are taking a difference of the pixel value, squaring it, summing it, taking an under root. So that's how you compute a Euclidean distance. But notice if the pixels are similar, for example, if x0 and y0 are similar, then this difference is going to turn out to be 0. And 0 squared will remain 0. So the more close, the closer these values are with each other, that goes on to reflect that the images are similar in nature with each other. There are many different features that could be used to identify similarity between images. Euclidean distance is one of them, Manhattan distance is another, city block distancing is another. So you have different kinds of distances that could be used, or different types of features that could be used to define similarities, or in formally, very strictly speaking, to find your nearest neighbors of our test image. So this is what we're going to do. We're going to find the difference between the first pixel, then we're going to do it for the second pixel, for the third, fourth, and so on, all the way for the last pixel. And for each difference, I'm going to square it and sum it, and the resultant sum would be taken in a square root. And that will give us a Euclidean distance. We're going to do the same thing for all of the images and then find out which Euclidean distance is the smallest. And that image is going to be the closest image, or the most similar image to our test image. So that is what the pipeline is. That is going to be the closest match in our data set, and that is what we are interested in doing. Let's have a look at how to do this in Python. You may want to head into Google Colab for this. Once you go into Google Colab, you may be tempted to create a new notebook, and you remember you would need to be signed into your Google account, and once you're in your notebook, you would have something set up like this. Also, you would be required to sign in to your Google Drive with the same Google account that you use to sign in with your Google Colab. In your Google Drive, I would request you to put in the data.mat. This contains our 50 images that are vectorized, and we also have a test image that we want to see and find the closest match in our dataset. So let's go through the code very quickly and understand how it goes about. We are importing different libraries in different areas of the code, but essentially this is the way to load your dataset from your Google Drive. Notice how we make use of functions from SciPy IOs, but notice how I have given the path for my Google Drive. So up until here, this is my Google Drive, and within my Google Drive I have a folder named as KNN. So this is my Google Drive, and I have a folder named as KNN. So you make sure you have the right path set up here. So once you have set that path up, we are just adding this string data.mat. This is the name of our data file, and we store that into dataset. Let's just go ahead and run it and see what we get. So it says drive already mounted, but if you're doing it for the first time, it might require verification on your Google Drive. So it would lead you towards a link on your Google Drive to get some access permissions and give you a token which you will copy and place back here, and then it should be ready to go. Once you're done, what we are interested in, we're just storing in the images in our images original variable, we store in the labels as well. And then I'm interested in looking at the shape of our dataset images. So if you look at the shape, that's the way to just go ahead and print and identify the shape of our variable images original, in which we had all our dataset. And the shape turns out to be 50, 3072. So we have 50 rows, 3072 columns. We've set up 50 images, and each image has 3072 pixels. All right, let's move on and see what have we got here. So we want to transpose this in order to reshape it. So reshaping here requires that we first transpose our data set. Once we have transposed it, we have seen the shape again. The shape of the transposed data set is now 3072 by 50. So what we had originally, we've just simply transposed it. So we have 50 columns now, 50 columns representing 50 images. And for each column, we have 3072 pixels. All right. What we do here is we just reshape our dataset and store this reshaped dataset into IMGS images. We reshape it into 32 by 32 just to view, just to see what our dataset really looks like. Okay, so we might be working or processing everything on our original dataset, but here we just reshape it to view the image, because when you want to view the image, you would not be looking at a vector of 3072 cross 1. You would be looking at a 32 by 32 by 3 sized RGB colored image. Okay, and that is why we look at the shape again, and this time we see, okay, we indeed have 32 by 32 by 3, the 3 channels for red, green and blue, and we have 50 of such images. So once we're sure of what we have, we go ahead and plot all rows and all columns, all channels, but we chose 40th image in all of our 50 images, and we just decide to view that, and that is what we see. Again, we wanted to look at the shape of this 40th image, and that rightly turns out to be 32 by 32 by 3. Okay, so that's the kind of image that we have, and that is the 40th image in the data set. Alright, so that we know we can view the images in our dataset like that. Let's move on and see what have we got here. So we've got a test image. Remember, we've given a path. The path is for my drive, and then I've given a test image.jpg. I have the test image in my drive, and that is the way. Once you've given the path, we've set up the path, you just use the read command of cv2 function. I'm reading it, and then I'm plotting my I'm viewing my image. The problem with this image is it's rather blue in color. Basically, the color channels are inverted when you normally load image like that, but we have a function bgr to rgb. It's going to change the format of the channels from bgr into rgb. So that's the correct format that we want to view in, the rgb format. So we just make that transformation and we view the image again, and that gives us the correct colors for the image. So now we have the correct color of the image. This is in fact our test image. We want to find the closest image in our data set to this image. Okay, so what we want to do first is notice the size on this image. It's about 170, 180 by 310, 320. So that's a big image. But remember, the images in our data set were 32 by 32. Alright, so we want to resize this image into 32 by 32, and once we resize this image into as a 32 by 32 image, notice how there's some distortion into that, and that's justified because we are squeezing in the image towards this, and we're using the default interpolation schemes. So irrespective of what this is, we want to find the closest match of this image in our dataset. After resizing it, we reshape our image into a vector of size 3072 cross 1. Okay, so we have our 32 by 32 image. Now we vectorize it, store it in img3. So we have a vector of our image, and now we are going to compute Euclidean distance of this vector with all the vectors in our dataset, all the 50 vectors in our dataset. And then we will see which one has the minimum Euclidean distance, and that minimum Euclidean distance image would be the closest match. Okay, so how do we go about computing the Euclidean distance? So we define a function. This is the way to define a function in Python. DEF is the way you begin defining the function. You have a name of the function, you define the arguments, the colon is the syntax, then you do whatever you want to do in the function. We have a for loop set up as well, and then we set up a return value of the function. What should the function return if we call this function? So this is how we define, we're defining a Euclidean distance. We define a distance variable, we define a for loop, we set up a range, and the range, the variable I is going to traverse from 0 to all the way to the length of the row. And why do we want to do it? Because we wanted to compute the Euclidean distance, but for each pixel. So I is basically traversing each pixel in those 3072 length of pixels. Row 1 and row 2 are the two input images that we are going to feed to this function. So essentially we wanted to take the difference between the two pixels, row 1 and row 2. We take the difference of the ith pixel, we square it. This is the way to square it in Python. We square their difference, and remember we had to take the under root, but before we took the under root we had to sum all the squared differences. So we update the squared difference in the distance variable here, and we do it I number of times. So not I number of times, the length of row 1 number of times. We'll see what is the length of row 1. It should be 3072. So and I is going to move from 0, and then in the next iteration it's going to be 1, 2, 3, and all the way to 3072, so that each pixel in both images is, and there's a difference between them that's squared, and the sum is maintained in this variable. And when the for loop ends, you have a squared sum. So when the for loop ends, you have this sum of squares of differences of the two pixels. All that remains then is to take the under root of this, and that we do by taking a square root, and then we return this answer, and we're going to store it somewhere. But what I want to do here is I just want to comment that out and show you what len length does. It's going to give me the length of image 3, which is 3072. So range 3072 is what we are feeding in for I in this for loop. Now let's just see what that actually means. So instead of 3072, I've just put in 5 to show you what range what is range doing over here. So range 5 means, and then we're printing the value of I in the for loop. So that means I takes the value from 0 to 4 if you have range 5. So here we had range 3072, which means I is going to take the value from 0 to 3071, which is what we wanted to do here. We wanted I to take the value 0 all the way to 3071. Okay, so I will let you play with this later on, and we're going to move on with our function definition. And once we're done with the definition of our function, let's just go ahead and define an array of zeros. We fill in zeros in our distance. Now in dist, we are going to keep track of all, we're going to basically feed in the values of Euclidean distance of all 50 images. Okay, so there are 50 images, there should be 50 Euclidean distances from our test image to each of those images. Here we calculate Euclidean distance in a for loop. So we have for I in range 50, that means I is going to take values from 0 to 49. Okay, from 0 to 49, that means and we have, remember, we had 50 images in our original images variable. So we have 50 images, but we traverse them one by one. Let's just take it for the first iteration. The first iteration, I is going to have the 0 value. So 0 value here means it has the first image. So the first image and all the pixels in that vector 0 to 3072, all the pixels in that first image are stored in selected image variable. We feed in image 3 vector, we feed in selected image vector, we get the Euclidean distance, we store it in the ith value of this array, ith index of this array. Okay, so I is 0, so in the 0 index we have the first Euclidean distance. Then I goes to 1, and in Python the indices progress from 0 instead of 1. MATLAB starts with 1, 2, 3. In Python you have from 0, 1. So 0 and then 1. When the index is 1, you have the second image selected here, the vector of that image, and the vector of our test image, image 3. Find the Euclidean distance, store it in here, and we do it 50 times for all the images. Then we print all these distances. We print the minimum distance. Min is for the minimum value in this array. And then we find argmin. Argmin is for the minimum, the argument of the minimum value in this dist array. We store it in min dist. So that argument is stored here. And we also print it, index of the minimum distance. So that is going to give us, so we get our Euclidean distances, but the minimum distance in this array turns out to be 479, should be somewhere around here. Or yeah, here it is, 479. Okay, so we have a minimum distance. We figured out that this image is the closest match, but you want to know the index of this image in our dataset, and we figured that out, that it is the 43rd image. All that remains now is to view this image. Now let's go ahead and view the image. Our images are stored in 32 by 32 by 3 format in the imgs variable. So we're going to just have all rows, all 32 rows, all 32 columns, all 3 channels, and the min dist, the 43rd. Remember, min dist has the argument or index of the minimum distance. It's stored in min dist, so that's why we just feed in min dist here, so that it will get 43. So the 43rd image gets shown here. And if you are familiar with this face, it's pretty much the same personality as this. So that's one way to verify. Also, there are similarities in both images. Maybe the black hair would cause and would give you very small differences when computing Euclidean distances. So that could be one reason why distances are smaller. Anyways, this is the closest image that the algorithm has figured out. Another function that we have is argsort dist. So it sorts the dist array based on the minimum distance, based on the smallest values that we have. So 43rd, and these are indices. So 43rd index in the dist array has the smallest value in dist array. 6 has the next smallest, 29 has the next. So we've already seen 43rd. I'll leave you to see 6, 29, 41. So if I had to figure out 3 nearest neighbors of our test image, those would be these 3. If I had to figure out 5 nearest neighbors, those would be these 5. If I had to find k nearest neighbors, then those would be the k number of values. So that is about it regarding k nearest neighbors in a sense. We'll look forward to more applications later in time. For any questions, I'll be happy to answer them in the comments. Thank you.